What if I told you that somewhere in the universe, stars are racing through space so fast they could cross the entire Milky Way in just a few million years? Or that black holes can spin so rapidly they twist the fabric of space-time itself? These aren't just wild ideas, they're real, mind-bending phenomena happening right now in the cosmos. Welcome to a journey through the universe's most extreme speeds, where the rules of physics as we know them are pushed to their absolute limits. From the speed of light to hypervelocity stars and beyond, we're about to explore how these cosmic speed demons challenge everything we thought we knew about space, time, and reality. So buckle up, because by the end of this video, you'll see the universe in a whole new light. And trust me, it's going to blow your mind. Let's dive in. Now, let's kick things off with one of the most fundamental and mind-blowing facts about speed in the universe: the speed of light. Clocking in at an astonishing 299,792 kilometers per second, light holds the title of the universe's ultimate speed limit. This isn't just a random number, it's a cornerstone of physics that shapes our understanding of space, time, and reality itself. Albert Einstein's theory of relativity hinges on this cosmic speed limit, showing us that nothing in the universe can travel faster than light. Why? Because as objects approach the speed of light, their mass increases infinitely, requiring infinite energy to go any faster. Something that's simply impossible. To put this into perspective, consider this: the light you see from the sun isn't instantaneous. It actually takes about 8 minutes to travel the 150 million kilometers from the sun to Earth. That means if the sun were to suddenly vanish, we wouldn't even know it for those 8 minutes. The speed of light also plays a crucial role in how we observe the universe. When we look at distant stars or galaxies, we're essentially looking back in time, seeing them as they were thousands, millions, or even billions of years ago. This cosmic speed limit isn't just a rule, it's a window into the past, helping us unravel the mysteries of the universe. So, while it might seem like a simple number, the speed of light is anything but ordinary. It's the heartbeat of the cosmos, governing everything from the smallest particles to the largest galaxies. Now, let's shift gears and talk about another fascinating concept that governs how objects move in space: escape velocity. Escape velocity is the minimum speed an object needs to break free from a celestial body's gravitational pull without further propulsion. Think of it as the cosmic speed limit for leaving a planet or moon behind. For Earth, that magic number is 11.2 kilometers per second. That's over 40,000 kilometers per hour. To put it simply, if you want to launch a rocket into space and have it escape Earth's gravity completely, it needs to hit that speed. But here's where it gets even more interesting: escape velocity isn't the same everywhere. It changes depending on the size and mass of the celestial body. Take our moon, for example. Because it's smaller and less massive than Earth, its escape velocity is only about 2.4 kilometers per second. That's why astronauts on the moon could hop around so easily. It takes far less energy to overcome its gravitational pull. On the other end of the spectrum, Jupiter, the largest planet in our solar system, has an escape velocity of a whopping 59.5 kilometers per second. That's more than 5 times Earth's. Understanding escape velocity is crucial for space exploration. It determines how much fuel and energy are needed to launch spacecraft, and it influences the design of rockets and missions. For instance, missions to Mars have to account for both Earth's and Mars's escape velocities to ensure a successful journey. Without this knowledge, we wouldn't be able to send probes to distant planets or land rovers on alien worlds. So, while it might sound like a technical detail, escape velocity is one of the key factors that makes space exploration possible. It's the invisible force that shapes our ability to reach for the stars. Now, let's zoom out from our solar system and dive into the incredible world of hypervelocity stars. These cosmic speedsters are stars that travel at mind-blowing speeds, often exceeding 1,000 kilometers per second. To put that into perspective, that's more than 3 million kilometers per hour, fast enough to cross the entire United States in just a few seconds. But how do stars reach such extreme velocities? The answer lies in the immense gravitational power of supermassive black holes. When a star gets too close to a supermassive black hole, it can be flung out of its galaxy at incredible speeds. This happens because of a gravitational slingshot effect, where the black hole's intense pull accelerates the star to hypervelocity. Imagine a cosmic game of pinball where the black hole is the flipper and the star is the ball being launched across the galaxy. One of the most famous examples of these runaway stars is S5HVS1, a star racing through space at an astonishing 1,700 kilometers per second. That's so fast, it's on a one-way trip out of the Milky Way. Hypervelocity stars aren't just fascinating because of their speed, they also give us clues about the environments around supermassive black holes. By studying these stars, scientists can learn more about the forces at play in the hearts of galaxies. Plus, their trajectories can help us map the distribution of dark matter, the mysterious substance that makes up a significant portion of the universe. So, while hypervelocity stars might seem like cosmic oddities, they're actually key players in helping us understand the larger workings of the universe. Next up, we'll explore another high-speed phenomenon in space: pulsars, the cosmic lighthouses that spin at dizzying speeds. But for now, let's just marvel at the idea of stars racing through the cosmos, defying gravity and leaving their galaxies behind. It's a reminder that even in the vastness of space, there's no shortage of action and excitement. Now, let's shift our focus to another high-speed marvel of the universe: pulsars. These cosmic powerhouses are the remnants of massive stars that have exploded in supernova, leaving behind incredibly dense neutron stars. But what makes pulsars truly extraordinary is their mind-bending spin speeds. Imagine a star so compact that it spins hundreds of times every single second. That's right, some pulsars rotate faster than your kitchen blender. The rapid rotation of pulsars isn't just for show, it's what makes them shine. As these neutron stars spin, they emit intense beams of radiation from their magnetic poles. These beams sweep across space like the light from a lighthouse, earning pulsars their nickname as cosmic lighthouses. Every time a beam points toward Earth, we detect a pulse of radiation, which is how pulsars got their name. It's like the universe's way of sending us a blinking signal from across the cosmos. One of the most extreme examples of these spinning wonders is Pulsar J1748-2446 the fastest known pulsar. This cosmic speedster spins an astonishing 716 times per second. To put that into perspective, if you were standing on its surface, you'd be moving at nearly a quarter of the speed of light. That's so fast, it defies imagination. Pulsars aren't just fascinating because of their speed, they're also incredibly precise. Their pulses are so regular that scientists use them as cosmic clocks to study everything from gravitational waves to the structure of the Milky Way. In fact, the discovery of pulsars in the 1960s was so groundbreaking, it earned a Nobel Prize in physics. So, while pulsars might seem like distant, spinning oddities, they're actually invaluable tools for understanding the universe. Their rapid rotation and precise pulses remind us that even in the vastness of space, there's a rhythm and order to the chaos. And as we continue our journey through the universe's most extreme speeds, let's keep in mind that these cosmic lighthouses are lighting the way for discovery. Next, we'll dive into the high-speed world of relativistic jets, where particles race through space at nearly the speed of light. But for now, let's take a moment to appreciate the incredible precision and power of pulsars, nature's own spinning timekeepers. Now, let's zoom into one of the most dramatic displays of speed in the universe: relativistic jets. These are colossal beams of particles and radiation that shoot out from the vicinity of black holes and neutron stars, racing through space at nearly the speed of light. Picture a cosmic fire hose blasting energy across millions of light years, and you'll start to grasp the sheer power of these jets. Relativistic jets form when matter spirals into the intense gravitational pull of a black hole or neutron star. As this material gets sucked in, not all of it falls into the abyss. Instead, some of it gets funneled into narrow beams along the object's rotational axis, accelerated to mind-blowing speeds by powerful magnetic fields. These jets can stretch for thousands, even millions of light years, piercing through the fabric of space like cosmic arrows. What makes these jets truly awe-inspiring is the energy they carry. As the particles in the jets collide and interact, they emit intense radiation across the electromagnetic spectrum. From radio waves to gamma rays, this makes relativistic jets some of the brightest objects in the universe. In fact, quasars, which are powered by supermassive black holes, owe their incredible luminosity to these jets. They shine so brightly that they can outshine entire galaxies, making them visible from billions of light years away. But relativistic jets aren't just about raw power, they also play a crucial role in shaping the cosmos. As these jets travel through space, they interact with the surrounding gas and dust, heating it up and pushing it around. This process can trigger the formation of new stars or even halt star formation in certain regions, effectively sculpting the evolution of galaxies. In a way, these jets are like cosmic architects, influencing the structure and destiny of the universe on a grand scale. One of the most famous examples of relativistic jets comes from the galaxy Messier 87, home to the first black hole ever imaged by humanity. Its jet stretches over 5,000 light-years, a testament to the incredible forces at work near black holes. These jets remind us that even in the darkest corners of the universe, there's an extraordinary interplay of speed, energy, and creation. As we marvel at the sheer velocity and power of relativistic jets, we're reminded once again that the universe is a place of extremes. These jets are not just fleeting phenomena, they're cosmic engines, driving change and illuminating the mysteries of space. And as we continue our journey through the universe's most extreme speeds, let's keep our eyes on these dazzling beams of light, for they hold the key to understanding some of the most energetic processes in existence. Next, we'll explore how the universe itself is expanding faster than the speed of light, a phenomenon that challenges our very understanding of space and time. But for now, let's take a moment to appreciate the breathtaking spectacle of relativistic jets, nature's own particle accelerators racing across the cosmos at nearly the speed of light. Now let's shift our gaze to an even grander scale, the expansion of the universe itself. You might think the speed of light is the ultimate limit, but when it comes to cosmic expansion, the rules are a little different. The universe isn't just expanding, it's doing so at speeds that can exceed the speed of light. And here's the kicker, this doesn't break Einstein's theory of relativity. How? Because it's not objects moving through space, it's space itself that's stretching. This mind-bending phenomenon is driven by something called dark energy, a mysterious force that makes up about 68% of the universe. Dark energy acts like an anti-gravity, pushing galaxies apart at an accelerating rate. The farther apart two galaxies are, the faster they seem to move away from each other. At great enough distances, this expansion can outpace even the speed of light. But don't worry, this doesn't mean anything is breaking the cosmic speed limit. Instead, it's the fabric of space-time that's stretching, carrying galaxies along with it like raisins in an expanding loaf of bread. To measure this expansion, scientists use something called the Hubble constant. Named after astronomer Edwin Hubble, this constant tells us how fast the universe is expanding. Currently, the Hubble constant suggests that for every megaparsec, about 3.26 million light-years of distance, the universe expands by around 70 kilometers per second. That might not sound like much, but over vast cosmic distances, it adds up to staggering speeds. What does this mean for the future of the universe? If dark energy continues to dominate, the expansion will keep accelerating. Galaxies will drift farther and farther apart, eventually becoming so distant that their light will never reach us. In billions of years, the night sky might look very different, emptier and darker, as galaxies beyond our local group fade from view. This cosmic expansion is a reminder that the universe is not static. It's dynamic, evolving, and full of surprises. And while it might seem counterintuitive, it's a perfect example of how the universe operates on its own terms, bending the rules in ways that challenge our understanding. As we ponder the vastness of cosmic expansion, let's turn our attention to another marvel of speed, the fastest man-made object ever created. But for now, take a moment to reflect on the fact that the very fabric of space is stretching, carrying galaxies along at speeds that defy imagination. It's a humbling reminder of just how small we are in the grand tapestry of the cosmos. Now, let's zoom in from the vastness of cosmic expansion to something a little closer to home: human ingenuity. Meet NASA Parker Solar Probe, the fastest man-made object ever created. This incredible spacecraft travels at a mind-blowing speed of 700,000 kilometers per hour, or 195 kilometers per second, as it orbits the Sun. To put that into perspective, at that speed, you could travel from New York to Los Angeles in about 20 seconds. The Parker Solar Probe isn't just breaking speed records, it's on a groundbreaking mission to study the Sun's corona, the outermost layer of the Sun's atmosphere. The corona is a place of extreme temperatures reaching millions of degrees Celsius, and it's also the source of the solar wind, a stream of charged particles that flows out into the solar system. Understanding the corona is crucial because it affects space weather, which can impact satellites, communications, and even power grids here on Earth. But how does the Parker Solar Probe achieve such incredible speeds? The answer lies in gravity assists. By flying close to Venus, the probe uses the planet's gravity to slingshot itself closer to the Sun, gaining speed with each pass. It's like a cosmic game of pinball where Venus acts as the flipper, propelling the probe faster and faster. This clever use of gravity allows the Parker Solar Probe to get closer to the Sun than any spacecraft before it, enduring temperatures that would melt most materials. Equipped with a state-of-the-art heat shield made of advanced carbon composite materials, the probe can withstand temperatures of nearly 1,400 degrees Celsius while keeping its instruments at a comfortable room temperature. These instruments are designed to measure the Sun's magnetic fields, solar wind particles, and the structure of the corona, providing scientists with unprecedented data. The Parker Solar Probe is a testament to human curiosity and our desire to explore the unknown. By venturing closer to the Sun than ever before, it's helping us unlock secrets about our star and its influence on the solar system. And as it continues its daring journey, it reminds us that even in the face of extreme challenges, we can push the boundaries of what's possible. As we marvel at the Parker Solar Probe's achievements, let's turn our attention to another fascinating aspect of extreme speeds, this time in the realm of subatomic particles. But for now, take a moment to appreciate the incredible engineering and determination behind humanity's fastest spacecraft, racing through the solar system at speeds that defy imagination. Now, let's dive into the mysterious world of neutrinos, tiny, nearly massless particles that zip through the universe at speeds just shy of the speed of light. These ghostly particles are so elusive that they can pass through entire planets, stars, and even you without leaving a trace. In fact, trillions of neutrinos are streaming through your body right now, completely unnoticed. Neutrinos play a crucial role in some of the most explosive events in the cosmos, like supernova. When a massive star collapses and explodes, it releases an enormous burst of neutrinos, carrying away most of the star's energy. These particles are so efficient at escaping that they often reach us before the light from the explosion does. This makes neutrinos a key tool for astronomers studying the final moments of dying stars. But what makes neutrinos truly fascinating is their ability to travel through matter almost undisturbed. Unlike other particles, neutrinos rarely interact with anything, thanks to their incredibly small mass and lack of electric charge. This means they can travel vast distances across the universe without being slowed down or deflected. However, neutrinos haven't always been free from controversy. In 2011, the OPERA experiment made headlines when it appeared to detect neutrinos traveling faster than the speed of light. This finding, if true, would have upended our understanding of physics. But after much scrutiny, it turned out to be a measurement error caused by a loose cable in the equipment. While the results were ultimately debunked, the incident highlighted just how challenging it is to study these elusive particles. Neutrinos continue to captivate scientists, offering clues about the inner workings of stars, the nature of matter, and even the origins of the universe itself. As we uncover more about these ghostly travelers, we're reminded that even the smallest particles can hold the biggest secrets. With neutrinos leaving us in awe of their speed and mystery, let's shift our focus to another cosmic phenomenon: galactic rotation speeds, where entire galaxies spin at astonishing rates, defying our expectations. Now, let's turn our attention to the mesmerizing dance of galaxies, where entire systems spin at speeds that defy our expectations. Galaxies, those vast collections of stars, gas, and dust, aren't just static structures, they're dynamic, rotating entities. But here's the twist: stars at the outer edges of galaxies move much faster than they should, based on the visible matter we can observe. This puzzling phenomenon has left scientists scratching their heads for decades. To understand why this happens, we need to look beyond what we can see. The visible matter in a galaxy, stars, planets, and gas, simply doesn't provide enough gravitational pull to explain the speeds of these outer stars. So, what's holding these galaxies together? The answer lies in something invisible and mysterious: dark matter. Dark matter is a type of matter that doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, its gravitational influence is undeniable. Scientists estimate that dark matter makes up about 85% of all matter in the universe. It forms an invisible halo around galaxies, providing the extra gravitational pull needed to keep stars at the outer edges moving at such high speeds. Without dark matter, galaxies would simply fly apart. This discovery has revolutionized our understanding of the cosmos. It's not just about what we can see, it's about what we can't see. Dark matter is the cosmic glue that holds galaxies together, shaping the structure of the universe on the grandest scales. And while we still don't know exactly what dark matter is made of, its effects are impossible to ignore. As we marvel at the incredible speeds of galactic rotation, we're reminded that the universe is full of mysteries waiting to be unraveled. Next, we'll explore another high-speed cosmic phenomenon: the shockwaves from supernova, where particles are accelerated to near light speeds, creating some of the most energetic events in the universe. Now, let's shift our gaze to one of the most explosive events in the cosmos: supernova. When a massive star reaches the end of its life, it doesn't fade quietly. It goes out with a bang, unleashing a shockwave that ripples through space at unimaginable speeds. These shockwaves are so powerful that they can accelerate particles to nearly the speed of light, creating some of the fastest-moving objects in the universe. But how does this happen? When a star explodes, it releases an enormous amount of energy, sending a shockwave racing outward. As this shockwave travels, it slams into surrounding gas and dust, compressing it and heating it to extreme temperatures. This process acts like a cosmic particle accelerator, pushing electrons, protons, and other particles to incredible speeds. Some of these particles become cosmic rays, high-energy radiation that zips through space at nearly the speed of light. Cosmic rays are among the most energetic phenomena in the universe, and supernova shockwaves are one of their primary sources. These particles don't just stay in the vicinity of the explosion. they travel vast distances, influencing the chemistry and dynamics of interstellar space. When cosmic rays collide with atoms in space, they can trigger the formation of new elements, seeding the universe with the building blocks of stars, planets, and even life itself. The impact of supernova shockwaves extends far beyond the explosion itself. They shape the interstellar medium, the vast expanse of gas and dust between stars, by heating it and stirring it up. This process can trigger the formation of new stars, creating a cycle of stellar birth and death that keeps the universe dynamic and ever-changing. As we explore the incredible speeds generated by supernova shockwaves, we're reminded of the interconnectedness of the cosmos. These explosions aren't just destructive, they're creative forces, driving the evolution of galaxies and the universe itself. Next, we'll dive into the swirling chaos around black holes, where matter in accretion disks reaches mind-bending speeds, revealing yet another extreme aspect of our universe. Now, let's venture into the swirling chaos surrounding one of the universe's most mysterious objects, black holes. Imagine a cosmic whirlpool where matter spirals inward at unimaginable speeds, creating a spectacle of light and energy. This is the accretion disk, a ring of gas, dust, and other material orbiting a black hole, and it's here that particles reach some of the most extreme speeds in the universe. As matter falls toward the black hole, it doesn't plunge straight in. Instead, it forms a disk that spins faster and faster as it gets closer to the event horizon, the point of no return. In this disk, particles can reach speeds that are a significant fraction of the speed of light, creating a frenzied environment of heat and radiation. The closer the material gets to the black hole, the more energy it releases, heating up to millions of degrees and glowing brightly across the electromagnetic spectrum. But what powers this incredible display? Friction and magnetic fields play a crucial role. As particles in the disk collide and rub against each other, friction generates heat, turning the disk into a blazing inferno. At the same time, magnetic fields twist and stretch, channeling energy and accelerating particles even further. This combination of friction and magnetism not only heats the disk but also causes it to emit intense radiation, from X-rays to visible light, making accretion disks some of the brightest objects in the universe. These glowing disks aren't just a byproduct of a black hole's appetite, they are also windows into the extreme physics at play. By studying accretion disks, scientists can learn about the behavior of matter under conditions that are impossible to replicate on Earth. They reveal how black holes grow, how they influence their surroundings, and even how they can launch powerful jets of particles into space at nearly the speed of light. As we peer into the heart of these cosmic whirlpools, we're reminded of the incredible forces that shape our universe. Next, we'll explore how these same black holes send ripples through space-time itself, creating gravitational waves that travel at the speed of light and reveal the universe's most violent events. Now, let's shift our focus to one of the most groundbreaking discoveries in modern astrophysics: gravitational waves. These are ripples in the fabric of space-time itself, traveling outward at the speed of light from some of the most violent and energetic events in the universe. Imagine throwing a stone into a calm pond. The ripples that spread out are similar to how gravitational waves propagate through the cosmos, carrying with them the echoes of cataclysmic events like black hole collisions and neutron star mergers. The first direct detection of gravitational waves was made in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. This monumental achievement confirmed a prediction made by Albert Einstein over a century ago and opened up an entirely new way of observing the universe. Unlike light, which can be blocked or distorted by dust and gas, gravitational waves pass through everything, offering an unobstructed view of the events that create them. This makes them a powerful tool for studying phenomena that would otherwise remain hidden. One of the most dramatic sources of gravitational waves is the collision of two black holes. When these massive objects spiral toward each other, They warp space-time around them, sending out ripples that grow stronger as they get closer. By the time they merge, the resulting gravitational waves carry an immense amount of energy, equivalent to several times the mass of the Sun being converted into pure energy in a fraction of a second. LIGO detectors, located thousands of kilometers apart, are so sensitive that they can measure these ripples, even though they stretch and compress space by less than the width of an atom. But black hole mergers aren't the only events that produce gravitational waves. Neutron star collisions, supernova, and even the early moments of the Big Bang are thought to generate these ripples. Each type of event leaves a unique fingerprint in the gravitational wave signal, allowing scientists to piece together the story of what happened. For example, the collision of two neutron stars detected in 2017 not only produced gravitational waves but also a burst of light across the electromagnetic spectrum, providing a multi-messenger view of the event. Gravitational waves have revolutionized our understanding of the universe, offering a new way to explore its most extreme phenomena. They've allowed us to confirm the existence of black holes, measure their properties, and even test the limits of Einstein's theory of general relativity. As we continue to detect more of these ripples, we're uncovering the hidden symphony of the cosmos, one wave at a time. Next, we'll dive into the fastest star in the Milky Way, a cosmic speedster racing around our galaxy's supermassive black hole at breathtaking velocities. Now let's turn our attention to a true cosmic speedster, the fastest star in the Milky Way. Meet S4714, a star that races around the supermassive black hole at the center of our galaxy, Sagittarius, a star at an astonishing speed of 24,000 kilometers per second. To put that into perspective, that's about 8% the speed of light, a velocity so extreme it defies imagination. S4714's incredible speed is a direct result of the immense gravitational pull of Sagittarius, a star. This supermassive black hole, with a mass equivalent to 4 million suns, creates a gravitational field so intense that anything venturing too close is whipped into a frenzy of motion. S4714 orbits perilously close to the black hole, completing a full revolution in just a few years. At such proximity, the star experiences gravitational forces so strong that they stretch the very fabric of space-time, accelerating it to these mind-boggling speeds. But how does a star end up in such a high-speed orbit? Scientists believe that S4714 was likely part of a binary star system that wandered too close to Sagittarius, a star. The black hole's gravity would have torn the pair apart, capturing one star while flinging the other away at incredible speeds. The captured star, now S4714, was left in an extremely tight and fast orbit, making it one of the most extreme objects in our galaxy. This star isn't just a curiosity, it's a valuable tool for astronomers. By studying its orbit, scientists can test the predictions of Einstein's theory of general relativity in one of the most extreme environments in the universe. The way S4714 moves around Sagittarius, a star, provides insights into the behavior of matter and gravity near a supermassive black hole, helping us better understand these enigmatic objects. S4714 is a reminder of the incredible forces at work in our galaxy, where stars can be flung to unimaginable speeds by the sheer power of gravity. Next, we'll explore the high-energy particles known as cosmic rays, which travel through space at nearly the speed of light, carrying secrets from some of the universe's most violent events. Now, let's shift our focus to one of the universe's most elusive travelers, cosmic rays. These high-energy particles zip through space at nearly the speed of light, carrying with them the secrets of some of the most violent events in the cosmos. But what exactly are cosmic rays and where do they come from? Cosmic rays are not actually rays at all, they're tiny particles, mostly protons and atomic nuclei, that have been accelerated to incredible speeds. These particles are thought to originate from some of the most energetic phenomena in the universe, such as supernova, the explosive deaths of massive stars, or the active galactic nuclei of distant galaxies, where supermassive black holes unleash unimaginable amounts of energy. When a star explodes in a supernova, the shockwaves can propel particles to nearly the speed of light, sending them hurtling across the galaxy and beyond. But cosmic rays don't just stay in space, they also interact with Earth. When these high-energy particles collide with our planet's atmosphere, they create a cascade of secondary particles, some of which reach the ground. This interaction is not just a scientific curiosity, it has real-world implications. For example, cosmic rays can affect satellite electronics, disrupt communication systems, and even influence cloud formation, potentially impacting Earth's climate. Studying cosmic rays is no easy task because they're charged particles. Their paths are bent by magnetic fields as they travel through space, making it difficult to trace their exact origins. However, scientists use advanced detectors like those at the Pierre Auger Observatory to study these particles and piece together their cosmic journeys. By understanding cosmic rays, we gain insights into the processes that accelerate particles to such extreme speeds and the role these particles play in shaping the universe. Cosmic rays are a reminder that even the smallest particles can carry the energy of the universe's most powerful events. Next, we'll dive into the mystery of the Great Attractor, a gravitational anomaly that's pulling galaxies toward it at incredible speeds, reshaping our understanding of the cosmos. Now, let's turn our attention to one of the most intriguing mysteries in the cosmos, the Great Attractor. Hidden in the depths of space, this massive gravitational anomaly is pulling entire galaxies, including our own Milky Way, toward it at staggering speeds of 600 kilometers per second. But what exactly is the Great Attractor, and why is it so difficult to study? The Great Attractor lies in the direction of the constellation Centaurus, roughly 250 million light-years away. Despite its immense gravitational pull, it remains shrouded in mystery because of its location behind the Milky Way's galactic plane. This region is filled with dense clouds of gas and dust, which block our view and make it nearly impossible to observe directly using visible light. It's like trying to see a distant lighthouse through a thick fog. The light is there, but it's obscured by the haze. Scientists believe the Great Attractor is a massive concentration of matter, possibly a supercluster of galaxies, exerting a gravitational force strong enough to influence the motion of galaxies across vast distances. This phenomenon challenges our understanding of the universe's large-scale structure and raises questions about what else might be hidden in the cosmic shadows. Studying the Great Attractor requires innovative techniques. Astronomers rely on instruments that can peer through the Milky Way's dust using wavelengths like infrared and radio waves. These tools have revealed glimpses of the galaxies being pulled toward the anomaly, but much about the Great Attractor remains unknown. Is it a single massive structure, or is it part of an even larger cosmic web? The answers could reshape our understanding of how galaxies move and interact on the grandest scales. The Great Attractor is a reminder that even in an age of advanced technology, the universe still holds secrets just out of reach. Next, we'll explore the fastest known exoplanet, a world orbiting its star so closely that it completes a year in just 26 hours, defying our expectations of planetary motion. Now, let's zoom in on a world that defies everything we know about planetary motion, WASP-12b, the fastest known exoplanet. Imagine a planet so close to its star that it completes an entire year in just 26 hours. That's right, a year on WASP-12b is shorter than a single day on Earth. This blistering speed is just one of the many mind-bending features of this extreme world. WASP-12b is what astronomers call a hot Jupiter, a gas giant that orbits incredibly close to its parent star. In fact, it's so close that the planet is practically hugging its star with a distance of only about 3 million kilometers. That's less than 1/10 the distance between Mercury and our Sun. This proximity creates an environment that's as hostile as it is fascinating. The intense heat from the star bombards WASP-12b, heating its atmosphere to a scorching 2,200 degrees Celsius. That's hot enough to vaporize metals like iron and titanium. But the extreme temperatures aren't the only challenge this planet faces. The gravitational pull from its star is so strong that it stretches WASP-12b into an egg-like shape, a phenomenon known as tidal distortion. These tidal forces are so powerful that they're literally ripping the planet apart. Over time, WASP-12b is losing its atmosphere, with streams of gas being pulled away into space. Scientists estimate that this exoplanet could lose a significant portion of its mass over the next 10 million years, a blink of an eye in cosmic terms. WASP-12b is a stark reminder of how diverse and extreme planetary systems can be. Its rapid orbit and extreme conditions challenge our understanding of how planets form and evolve. Next, we'll dive into one of the most energetic events in the universe: gamma-ray bursts, which release more energy in seconds than the Sun will in its entire lifetime. Now, let's shift our focus to one of the most explosive and fleeting phenomena in the cosmos: gamma-ray bursts. These are the universe's ultimate powerhouses, capable of releasing more energy in just a few seconds than our Sun will emit over its entire 10 billion-year lifespan. To put that into perspective, imagine the energy of 1 billion suns concentrated into a single, blinding flash. That's the sheer scale of a gamma-ray burst. These bursts originate from some of the most violent events in the universe. One common source is the collapse of a massive star at the end of its life. When a star many times more massive than our Sun exhausts its fuel, its core collapses under its own gravity, triggering a supernova. But in some cases, the collapse doesn't stop there. Instead, it forms a black hole, and in the process, jets of energy are launched outward at nearly the speed of light. These jets, packed with gamma rays, are what we detect as a gamma-ray burst. Another source of these bursts is the collision of two neutron stars. Neutron stars are the incredibly dense remnants of supernova, and when two of them spiral into each other, the resulting collision sends shockwaves through space-time and produces a spectacular burst of gamma rays. These events are so powerful that they can briefly outshine entire galaxies. What makes gamma-ray bursts even more fascinating is their unpredictability. They can occur anywhere in the universe and last anywhere from a few milliseconds to several minutes. Because they are so brief, detecting them requires precise timing and a bit of luck. Satellites like NASA, Swift, and Fermi are constantly scanning the skies, waiting to catch these fleeting cosmic fireworks. Despite their rarity, gamma-ray bursts have a profound impact on our understanding of the universe. They serve as cosmic beacons, allowing astronomers to study the most distant reaches of space. They also provide clues about the life cycles of stars, the formation of black holes, and even the nature of gravity itself. As we move forward, let's turn our attention to another cosmic speedster, the Andromeda Galaxy, which is racing toward the Milky Way at 110 kilometers per second, setting the stage for a galactic collision billions of years in the future. Now, let's zoom out from the fleeting brilliance of gamma-ray bursts and take a look at a cosmic event unfolding on a much grander scale: the inevitable collision between the Andromeda Galaxy and our own Milky Way. Picture this: Andromeda, our closest galactic neighbor, is hurtling toward us at an astonishing speed of 110 kilometers per second. That's fast enough to travel from Earth to the Moon in less than an hour. But don't worry, this galactic rendezvous won't happen anytime soon. In fact, it's set to occur in about 4.5 billion years. When these two galaxies finally meet, it won't be a catastrophic crash as you might imagine. Instead, it will be more like a slow, graceful dance. Galaxies are mostly empty space, so the stars within them are unlikely to collide directly. Instead, the immense gravitational forces at play will pull and twist the galaxies into new shapes, merging them into a single, larger galaxy. Astronomers have even given this future galaxy a name, Milcomda. During this cosmic merger, the night sky as we know it will transform dramatically. As Andromeda draws closer, it will grow larger and brighter in our sky, eventually stretching across the horizon. Over billions of years, the two galaxies will intertwine, their stars and gas clouds swirling together in a dazzling display of cosmic choreography. But what does this mean for our solar system? While the collision will reshape the Milky Way and Andromeda, our Sun and its planets are unlikely to be directly affected. The vast distances between stars mean that the chances of our solar system being disrupted are incredibly slim. However, the Sun's position within the new Milcomda galaxy could change, potentially altering our view of the cosmos. This collision isn't just a distant spectacle, it's a reminder of the dynamic and ever-changing nature of the universe. Galaxies collide and merge all the time, and these events play a crucial role in shaping the cosmos as we know it. They trigger the birth of new stars, fuel the growth of supermassive black holes, and drive the evolution of galaxies over billions of years. As we marvel at the future of our galaxy, let's turn our attention to another cosmic speedster, the fastest spinning black hole ever discovered, where space and time are stretched to their limits. Now, shifting our gaze from the grand dance of galaxies to the intense whirl of a single cosmic powerhouse, let's dive into the realm of the fastest spinning black hole ever discovered, Joris 1915 + 105. This black hole is a true speed demon, spinning at an astonishing rate of over 1,000 times every second. To put that into perspective, imagine a record player spinning so fast that it completes more than 1,000 full rotations in the time it takes you to blink. That's the kind of mind-bending speed we're talking about here. But what makes this black hole spin so extraordinary? As it rotates, it drags the very fabric of space and time around with it, a phenomenon known as frame dragging. This extreme distortion of space-time creates a swirling vortex that can accelerate matter to incredible speeds, launching powerful jets of energy and particles into space. These jets, known as relativistic jets, travel at speeds close to the speed of light, stretching across vast distances and lighting up the cosmos with their brilliance. The energy released by Joris 1915 + 105 is so immense that it can outshine entire galaxies. These jets are not just spectacular to observe, they also play a crucial role in shaping their surroundings. By heating up and pushing away surrounding gas and dust, they influence the formation of stars and even entire galaxies. What's truly fascinating is how this black hole's spin is a testament to the extreme conditions that exist in the universe. It's a reminder that even in the vast emptiness of space, there are pockets of unimaginable energy and motion where the laws of physics are pushed to their limits. As we marvel at the sheer power of Joris 1915 + 105, let's take a moment to appreciate the incredible forces at play in our universe. From the slow, graceful mergers of galaxies to the dizzying spins of black holes, the cosmos never ceases to amaze. And speaking of cosmic wonders, our next stop takes us to the outer edges of our solar system, where icy objects drift at surprisingly slow speeds until they're not. Now, let's journey from the dizzying spins of black holes to the serene, icy outskirts of our solar system, where the Oort cloud quietly resides. This vast, mysterious region is home to countless icy objects, drifting at speeds of just a few kilometers per second. To put that into perspective, these objects move so slowly that it would take them thousands of years to travel the distance light covers in a single second. But don't let their sluggish pace fool you. These icy wanderers hold secrets to the early days of our solar system. The Oort cloud is like a cosmic freezer, preserving remnants of the material that formed the Sun and planets billions of years ago. These icy bodies, often no larger than a few kilometers across, orbit the Sun at such great distances that they're barely influenced by its gravity. Yet, every so often, a passing star or the gravitational tug of the Milky Way can nudge one of these objects out of its orbit, sending it on a journey toward the inner solar system. As these icy travelers fall toward the Sun, something remarkable happens. The Sun's gravity accelerates them, transforming these slow-moving objects into blazing comets. By the time they reach the inner solar system, they're racing at hundreds of kilometers per second, their icy surfaces vaporizing to form spectacular tails that stretch across the night sky. This transformation from a slow, distant wanderer to a fast-moving comet is a reminder of how gravity shapes the motion of objects in our solar system. It's also a testament to the dynamic nature of the cosmos, where even the most seemingly inert objects can become agents of change. The Oort cloud may be far from Earth, but its influence is felt every time a comet streaks across our skies. These icy visitors not only provide stunning celestial displays, but also carry clues about the origins of our solar system. As we continue to explore the mysteries of the Oort cloud, we uncover more about the forces that have shaped our cosmic neighborhood. And speaking of cosmic forces, our next stop takes us to a binary star system where two white dwarfs orbit each other at breakneck speeds, creating ripples in the fabric of space-time. Now, shifting our gaze from the icy depths of the Oort cloud, we arrive at a cosmic dance of incredible speed and precision. Meet Cancri, the fastest known star system in the universe. This binary system is made up of two white dwarf stellar remnants so dense that a teaspoon of their material would weigh as much as an elephant. But what truly sets Cancri apart is the breathtaking speed at which these two stars orbit each other. Every 5.4 minutes, they complete a full orbit, racing around their shared center at an astonishing 600 kilometers per second. To put that into perspective, imagine two stars, each as massive as our Sun, whirling around each other at speeds faster than a bullet. Their close proximity and rapid motion create ripples in the fabric of space-time, known as gravitational waves. These waves, first predicted by Albert Einstein over a century ago, are like cosmic echoes, carrying information about the most extreme events in the universe. The gravitational waves emitted by Cancri are so powerful that they can be detected by observatories here on Earth. These ripples not only confirm Einstein's theory of general relativity, but also provide scientists with a unique window into the behavior of matter under extreme conditions. The intense gravitational forces at play in Cancri also cause the stars to slowly spiral closer together, losing energy with each orbit. Over millions of years, this dance will culminate in a spectacular collision, potentially triggering a supernova or forming an even more exotic object like a neutron star. Cancri is a testament to the dynamic and ever-changing nature of the universe. It reminds us that even in the vastness of space, objects can interact in ways that defy our imagination, creating phenomena that challenge our understanding of physics. As we continue to study systems like Cancri, we uncover more about the forces that govern the cosmos and the incredible speeds at which celestial objects can move. And as we marvel at the rapid orbits of these white dwarfs, our next stop takes us to the mysterious force driving the universe's expansion, dark energy. Now, as we leave behind the rapid orbits of Cancri, let's turn our attention to one of the most profound mysteries in the cosmos, dark energy. This enigmatic force is not only shaping the universe but also driving its expansion at an ever-increasing pace. Unlike gravity, which pulls objects together, dark energy works in the opposite direction, pushing galaxies apart and stretching the very fabric of space itself. Scientists first discovered the effects of dark energy in the late 1990s when they observed distant supernovae. These exploding stars appeared dimmer than expected, suggesting that the universe was expanding faster than previously thought. This revelation turned our understanding of the cosmos on its head. Instead of slowing down due to gravity, the universe's expansion was speeding up, and dark energy was the culprit behind this acceleration. But what exactly is dark energy? The truth is, we don't fully know. It's invisible, doesn't interact with light, and can't be detected directly. What we do know is that it makes up about 68% of the universe's total energy content, dwarfing the contributions of ordinary matter and even dark matter. One leading theory suggests that dark energy is a property of space itself, often referred to as the cosmological constant. According to this idea, empty space isn't truly empty. It contains energy that drives the universe's expansion. On cosmic scales, dark energy's influence is undeniable. It counteracts the pull of gravity, preventing galaxies from clumping together as much as they otherwise would. Over billions of years, this relentless push has caused the universe to grow larger and more diffuse. In fact, if dark energy continues to dominate, the universe could expand forever, leading to a future where galaxies are so far apart that they become invisible to one another. The mystery of dark energy challenges our understanding of physics and raises profound questions about the ultimate fate of the universe. Why does it exist? How does it work, and what does it mean for the cosmos as a whole? As scientists continue to study this elusive force, they hope to uncover clues that could revolutionize our understanding of space, time, and the very nature of reality. With dark energy shaping the universe's destiny, our next journey takes us to the heart of a cosmic phenomenon where particles race at near light speeds, the pulsar wind nebula of the Crab Nebula. Now, shifting our gaze to one of the most dynamic and visually stunning phenomena in the cosmos, we arrive at the Crab Nebula. At its heart lies a pulsar, a rapidly spinning neutron star that powers an extraordinary cosmic engine known as a pulsar wind nebula. This pulsar, the remnant of a supernova explosion observed on Earth in the year 1054, spins around 30 times every second, sending out a relentless stream of charged particles. These particles are accelerated to mind-boggling speeds, reaching close to the speed of light, creating what we call the pulsar wind. As these high-speed particles collide with the surrounding gas and magnetic fields, they produce a spectacular display of light and radiation. The glowing filaments of the Crab Nebula, visible in telescopes, are the result of this intense interaction. These filaments are not just beautiful, they're also a testament to the incredible energy being unleashed by the pulsar. The particles emit synchrotron radiation, a type of light produced when charged particles spiral around magnetic fields at near light speeds. This radiation spans the entire electromagnetic spectrum, from radio waves to gamma rays, making the Crab Nebula one of the brightest and most studied objects in the sky. The Pulsar Wind Nebula is a cosmic powerhouse constantly feeding energy into its surroundings. It's a vivid reminder of how extreme speeds and magnetic fields can shape the universe in dramatic ways. The Crab Nebula's pulsar wind not only illuminates the remnants of the supernova, but also provides scientists with a natural laboratory to study the behavior of matter and energy under extreme conditions. As we continue to unravel the mysteries of this celestial marvel, we gain deeper insights into the forces that drive the universe's most extreme phenomena. With the Crab Nebula's pulsar wind showcasing the incredible speeds of cosmic particles, our next stop takes us to the motion of our own galaxy, the Milky Way, as it hurtles through space at astonishing velocities. Now let's zoom out from the Crab Nebula and take a look at the bigger picture, our very own galaxy, the Milky Way. Did you know that our galaxy isn't just sitting still in space? In fact, it's racing through the cosmos at an astonishing speed of 2.1 million kilometers per hour, or 600 kilometers per second, relative to the cosmic microwave background. That's the faint afterglow of the Big Bang, which serves as a universal reference point for measuring motion in the universe. But what's propelling the Milky Way at such incredible speeds? The answer lies in the gravitational forces at play. Our galaxy is part of a cluster of galaxies called the Local Group, which includes Andromeda, the Triangulum Galaxy, and dozens of smaller galaxies. Together, these galaxies are being pulled by the gravitational influence of something even larger. The Great Attractor, this mysterious region located about 250 million light-years away, exerts a powerful gravitational pull, drawing galaxies toward it like a cosmic magnet. The Great Attractor is shrouded in mystery because it lies behind the dense plane of the Milky Way, making it difficult to observe directly. Scientists believe it could be a massive concentration of dark matter or a supercluster of galaxies. Whatever it is, its gravitational pull is so strong that it's shaping the motion of not just the Milky Way but countless other galaxies in our cosmic neighborhood. This movement isn't just a random drift, it's part of the intricate dance of gravity that governs the universe. As the Milky Way hurtles through space, it's also rotating, with stars, planets, and gas clouds swirling around its center. This combination of motion, both through space and within the galaxy, creates a dynamic, ever-changing cosmic landscape. Understanding the Milky Way's speed and trajectory gives us a glimpse into the larger forces shaping the universe. It's a reminder that even on the grandest scales, gravity reigns supreme, pulling galaxies together and driving the evolution of the cosmos. And as we continue to map these movements, we uncover more about the universe's past, present, and future. With the Milky Way's incredible journey through space in mind, our final stop brings us to the fastest known quasar, where jets of matter race through the cosmos at nearly the speed of light. Now, let's turn our attention to one of the most extreme speedsters in the universe, quasar 3C273. This cosmic powerhouse is not just any quasar, it's the fastest known quasar, with jets of matter blasting through space at an astonishing 99.9% the speed of light. To put that into perspective, these jets are moving so fast that if you could ride one, you'd circle the Earth nearly 7.5 times in just 1 second. So, what exactly is a quasar? At its heart lies a supermassive black hole, millions to billions of times more massive than our Sun. As matter spirals into the black hole, it forms a swirling disk of gas and dust called an accretion disk. The friction and magnetic forces within this disk heat it to incredible temperatures, causing it to glow brighter than entire galaxies. But that's not all. Some of this material gets funneled into powerful jets that shoot out from the black hole's poles at nearly the speed of light. Quasar 3C273, located about 2.4 billion light-years away, is a prime example of this phenomenon. Its jets stretch across thousands of light-years, emitting intense radiation that can be detected across the universe. These jets are not just spectacular to observe, they play a crucial role in shaping their host galaxies. As the jets plow through surrounding gas and dust, they trigger star formation and influence the structure of the galaxy itself. But quasars like 3C273 are more than just cosmic speed demons, they're also time capsules. Because light takes time to travel, observing quasars allows us to peer back into the early universe when galaxies were still forming and evolving. By studying these ancient beacons, scientists can piece together the story of how galaxies grow and change over billions of years. Quasar 3C273 reminds us that even in the vastness of space, speed and power are intertwined. Its jets, racing at nearly the speed of light, are a testament to the incredible forces at work in the universe. And as we continue to study these cosmic marvels, we uncover more about the dynamic processes that shape the cosmos. With this final fact, we've journeyed through some of the universe's most extreme speeds, from the speed of light to hypervelocity stars, pulsars, and beyond. Each of these phenomena reveals a different facet of the universe's incredible dynamism, challenging our understanding and sparking our curiosity. Which of these cosmic speed records amazed you the most? Let us know in the comments below, and don't forget to subscribe for more mind-blowing explorations of the universe's mysteries. Until next time, keep looking up. As we wrap up this journey through the universe's most extreme speeds, it's clear that the cosmos is a place of incredible dynamism and wonder. From the speed of light, the ultimate cosmic speed limit, to hypervelocity stars racing through galaxies at thousands of kilometers per second, each fact we've explored reveals a unique aspect of the universe's boundless energy and motion. We've marveled at pulsars spinning hundreds of times per second, relativistic jets blasting from black holes, and even the mind-bending expansion of space itself, driven by dark energy. These phenomena remind us that the universe is not static. It's a vibrant, ever-changing tapestry of forces and speeds that challenge our understanding and ignite our curiosity. Whether it's the Parker Solar Probe breaking records as the fastest human-made object or the Great Attractor pulling galaxies toward it at incredible speeds, each discovery underscores the sheer scale and complexity of the cosmos. And let's not forget the cosmic time capsules like Quasar 3c 273, whose jets travel at nearly the speed of light, offering us a glimpse into the universe's distant past. So, which of these extreme speeds left you the most amazed? Was it the mind-boggling spin of the fastest pulsar, the explosive power of gamma-ray bursts, or the mysterious pull of the Great Attractor? Let us know in the comments below. We'd love to hear your thoughts. If you enjoyed this cosmic adventure, don't forget to hit the like button, subscribe to our channel, and ring the notification bell so you never miss out on more mind-blowing explorations of the universe's mysteries. Thanks for joining us on this journey through the fastest phenomena in the cosmos. Until next time, keep looking up and stay curious.